Excel assignments, but I didn't finish yet. So hopefully I'll finish those soon. Oh yeah, right. Yeah, okay. 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 Any other questions? No? Okay. Okay. So today we'll look at some more examples of this binomial distribution. Okay. And so what is it, right? It's a family of discrete probability distributions. And so it has basically the same structure, and the family is different, made different by n and p. N being sort of the number of times that a experiment or that a process is repeated, and p is this probability of success. So there's always some probability of success, and then 1 minus p would be the complement, which is the probability of failure. And sometimes that's called q. And so, right, so q is the complement, is 1 minus p. Okay? And there are two views of the distribution. So this is sort of its name, the binomial distribution NP. And there's the probability mass function view, and there's also the continuous distribution function view, or the CDF view. Okay? And it turns out that it's possible to compute each of these probabilities with this kind of a formula. And so we'll see if we can go through that today for the probability mass function. And then the CDF, the continuous distribution function, is just really adding those up. So this is an individual, probability, like what's the probability that it equals 2? Or what's the probability that there are 4 heads out of, 10 trials, or something like that. And so this is one of the terms, those spikes, or those jumps, or those points. And then here is where, as you add them up, it jumps, it's a certain amount, and then when you reach the next integer, it jumps up by this amount, it jumps up by this amount, it jumps up by this amount. And this is basically saying that it adds it up. Okay, and so sometimes in finance classes, you really have to add up all of these things. And so this capital sigma, or this summation formula, is really a compact shorthand notation. So, you should just get used to seeing it, particularly for Business 314 Finance. And all it means is that there are these terms that you add up. And so here, to get the probability that it's less than or equal to a certain amount, you basically start k equals 0. So you index it from the beginning, you go up to r, go up to that point, and you just add up these probabilities. And oh, by the way, the formula for each of those individual probabilities is something like this. And so basically this is, a jump where, it's 0 in the beginning, and then once you hit 0, it jumps up by that amount, and then the next time you hit the next integer, r is, the index k goes to 1, it jumps up again and jumps. So this is basically what a step function looks like. Okay? And this is the one that sometimes people call it a comb, where it's, really 0, and it just sort of jumps up by a certain amount. So it's not, comb would be flat, where all the values are, say, 0.2 or 8 or something. Here they kind of have some, rigid structure, but still, because it's, mostly 0 and just in a few places spikes up, people sometimes call this one the comb function. Okay, and so we talked about the definition of the mean. This is sort of oops, I think I should actually have, the value times the probability at x. Okay. So this, well, no. That's actually okay. This means basically add up the values and divide by their by the total of them. But you could also sum of the value times the probability. at k. Okay, and what's actually very, very important is, since we're dealing mostly with the binomial distribution, instead of having to do this over and over and over for the binomial distribution, it's just NP. So we'll look at that. So this is a shorthand for the expectation. So anytime you have a binomial random variable, the average or the mean is NP, and we'll talk about that. And then there's this other, and so that tells you the center, right? The mean tells you the center, and then the variance gives you the spread, right? And so, you know, if you think of a quiz score or a set of test scores as, you know, a bunch of numbers, one of the first things that people like to know is what's the mean, what's the average, and then they might like to know what's the minimum and what's the maximum, what's the lowest, what's the high. Another measure of the spread would be the variance, so that kind of tells you how far away, kind of on average, are these mean squared things. So you take each one and you subtract it from the mean, which is the center. So now this is like a delta. You kind of have this process to square it so that they're all positive, and then you take this average delta, the squared delta. But it's squared, so then you actually take the square root of it, and then it becomes something that you can use. And so it turns out that for the binomial distribution, this variance is NPQ, basically. So where the average had a special, or the average had a special form NP, the variance is just NPQ, and remember that Q is equal to 1 minus P. So you can say it's N times P times 1 minus P, or you can say it's NPQ. So these are really the same. And then to get the standard deviation, right, the variance would be sigma squared. To get the standard deviation, you just take the square root. Okay, so we'll kind of go through some of those in more detail, right? Okay, so what do the following problems have in common, right? So we sort of looked at this last time, right? Suppose you're planning, oh no, not this one, a slightly different one. Okay, anyway, so suppose you're planning an event and you need 3 helpers. Oh, yeah. Maybe there's a wedding and you need 3 ushers, right? Someone else has already picked up the helpers for you, picked out or selected the helpers for you, but you know these people have a 50-50 chance of showing up. What's the probability that all 3 show up? So maybe, you know, you might want to know, how likely should I have some backups, you know, just in case, right? What's the likelihood that 2 of them show up? You know, so maybe I should have 1 really solid backup, and then I should have, you know, a second backup just in case, maybe for planning, right? Making decisions. Okay, so another example. Suppose that there are 3 customers in a customer service line. From past experience, say from empirical studies, right, you know that the probability that a customer will need to talk to a supervisor is 10%. So 1 in 10 cannot be handled by the frontline customer service representative and needs backup. So, you know, how likely should you have a manager on hand, right? If there are a few people there, probably you don't need a manager to be on hand. On the other hand, if you can see that there's a long queue of them, you know, maybe you should have a manager, instead of being, you know, far away, manager should try to do something in that area, because there's a possibility that they'll need to be called, right? So that's also, you know, it's kind of for planning. Now, suppose that there are 5 guests who've checked in at the front desk. There's a 95% chance that their luggage will be delivered to their room within 5 minutes of arrival. What is the probability that all 5 of the guests will have their luggage delivered, say, on time, within 5 minutes? So, what do these problems all have in common? What do you think about what these problems all have in common? Do they have anything in common? Or are they all different? oh, so in one of them they're asking, what's the probability they all, well, one thing they have in common is there's n things, right? So here it's 3 things, here it's 5 things, and then the final question is, what's the probability that they all happen within that time? Okay, so maybe, right, so maybe you would say one thing that you might observe is that there's this basic random experiment that has a binary, meaning, 0 or 1 has a binary, we'll say outcome. Right? So 0 or 1, heads or tails, on time, not on time. Okay, so maybe one thing we could say is that there's this basic random experiment, and maybe we'll say probability of success is P, and then we might say probability of failure Q, which is equal to 1 minus P, which is the complement. Okay, so if you look at all 3 of these, right, there's this basic underlying random experiment that's either yes or no, right? So the helpers are either show up or they don't show up. And there's a probability, 50-50, right, that they'll show up, and then 50 that they'll show up, and then complement 1 minus 50%, 50% Q, that they don't show up, right? So this sort of has that element in it. 3 customers in the customer service line. Here it is, they need to talk to a supervisor, or they don't need to talk to a supervisor, right? You can view it in that sense, they may have, some of them may take a long time, others may take a short amount of time, that's a different question. But if the question is, do they need to talk to a supervisor, and what's the likelihood, what's the chance that they need to talk to a supervisor? So there is that binary event, right? And then it's repeated in this time, there's 3 customers. So each of them is kind of like this experiment over and over. You could view it that way. Okay, and then 5 guests in the checkout line, checking in, and then they need their luggage delivered. It's either delivered within 5 minutes or it's not. Like the hotel wants to have a good service, right? They want the customers to be satisfied, and so their measure of are the customers satisfied or not are, is the luggage delivered within the service agreed time. Okay, so that's one element that they have in common, and then here. We observe that the probability that all 3 show up, they all show up. What's the probability they all show up, right? So the basic random experiment is repeated. Oops. N times. Okay, so it kind of goes over and over again. Okay, and it's repeated N times, and actually it turns out that each time it is repeated, it is, or the is repeated, the repeats are independent. Okay, so when the next person, so for example, it would not be independent if the three helpers were all friends or they're all in the same family, right? Because if they all come in the same car, then that's not independent, right? Because if the car comes, then all three of them will be there, right? If the family, gets there on time, then all three of them will be there, right? So here, independent means they're all independent. Like they're not carpooling together. One does not depend on the other, right? They're all independent. So if that's the case, right, then you can use this. Otherwise, if there's some correlation, there's some relationship, then it doesn't work, right? Here in the customer service line, right, you assume that it's not, three people, like all three of them have the same complaint, right? Like they bought something and it didn't work, and so they all said, you know what, we're all going to go down, we'll go down together. And so all three of them, then, they have the same problem, they all need to see a supervisor, that they're not independent, right? The 5 guests, each repeat of the experiment is going to be different, right? You assume that they're independent. And so that's actually an important assumption in order to use the binomial distribution to try to solve problems. Okay? Does that make sense? Okay, so we started to very briefly look at the 3 helpers case, right? The wedding. And so how would you do this, right? Hopefully, it's a little bit complicated. Hopefully you'd say, well, it's not cost, volume, profit, right? There's no interest rate, right? And there's no talking about any money, so we're not doing any time value of money. Something to do with probability. Okay, well, what do you need to talk about probabilities? Well, we define probabilities on these events, right? And then in order to be a little bit more sophisticated, right, you have a random variable. And so the random variable would be, the probability that all 3 of them show up, right? And so then you have a way to assign a number to each of the events. Okay, and so SSS, I guess, would be success, and failure would be that they did not show up on time. Okay, so then now that we have understand our sample space, right, all of the underlying events, next we have our random variable, right, and so this is our random variable for the sample space. Then the last thing, the final thing that we do is we kind of hook up, or we connect a probability distribution to this random variable. Okay, so now we're saying, well, actually, we'll assume that these are independent, and in all of these problems you do have to assume they're independent. So we will assume that they're all different. They're not roommates. They're not come in this blah blah blah. They're all different families, independent ways to get there, and so forth. Right. So then we can use the binomial distribution. In fact, we will use like this particular member of the family of the binomial distributions, the 3 1/2. So n equals 3, and the probability of success is equal to 1/2, right? This is also the same as a coin toss, right? 3 tosses of a fair coin, right? So in general, it will be BNP, and maybe there's 5 people, another way to do this would be to say, you really need 3 helpers, and so I'm going to ask 5 people. So if I ask 5 people, and they all have a 50-50 chance of showing up, what's the probability that I have 3 or more, right? Because then 3 or more would be, you have enough, right? If only 1 or 2 of your 5 come, you're not complete. You need 3 to show up, or 4 to show up, or 5 to show up, right? So that's a different question, right? So here, we'll stick with this one, right? And so, you base 3, what are the probabilities like? Okay. So here's this comb function, right, where, it's mostly 0, and then it kind of jumps up at each of these specific points. So that would be the probability mass function. Oh, sorry. This should be probability mass function. and this would be the CDF, the cumulative distribution function. Okay, and this is the step function one. So this is the one that sums up the previous one. Okay, and this one is easy, right? Because it's kind of like the fair coin, and so we have these values. Okay, so what is the probability that at least 2 show up? So here we ask a few more questions, right? We want to ask, what's the probability that at least 2 show up? What's the probability that 1 or 2 show up? Okay, and how many would you expect to show up? So what's the probability that at least 2 show up? Sorry? 40? 25%? Why? We should be a little more systematic, right? So what is the probability that at least 2 show up? How could we cast that in this framework? And so, you know, how do you think about this? You know, it's like there are all of these tools here, like, you know, a table saw or a, you know, drill press, kind of some sophisticated tools, you know, mathematical probability tools. And so what we want to do is we want to use some of these mathematical tools. We want to get some experience using these to construct answers, to build, you know, find the solution to some, you know, little bit more challenging problems, right? So we've set up all of this framework. So how can we use this framework to ask, what is the probability that at least 2 show up? How can we cast this and take advantage of all of this, you know, stuff that we have? What is it like? You know, it's almost like you're invited to this kind of foreign buffet. Like you go to a different country, and then somebody invites you to this buffet, and there's all this weird food there, and you know, if you like, try it, you might like it. You know, if you don't, so it's like all this stuff is just like sitting there, but you have to know how to use it. So that's the challenge, right? That's what we want to learn. We want to figure out how can, like, there's so much stuff. There's so many useful stuff that's just sitting here, but you know, how do you make sense of it, and how can you use it to help you answer a problem? That's what we want to learn. So what's the probability that at least 2 show up? Is there a way that we can count the number that show up? Find the probability that 1 shows up? Okay, so you know what? That's actually a start, right? What do we want? We want the probability that at least 2 show up, right? But, you know, that's actually really good, because if you don't know where to start, you have to start somewhere, right? And so we would want the probability that 1 shows up. So what's the probability that 1 shows up? Well, it's not exactly 1 out of 3, right? Because yes, it's 0.125. Why is it 0.125? Why is the probability that 1 shows up 0.125? Oh no, sorry. It's not. Sorry. I was looking at the wrong thing. It's not 0.125. What's the probability that 1 shows up? (0.375). Yes, that's correct. Because the probability that 1 shows up, it could be that the first one shows up and the other 2 don't show up. Or it could be that the second one shows up and the first one and the third one didn't show up. Or it could be that the third one showed up and the first 2 didn't show up. Right? And so here we have from this probability mass function, from this tool that we have, the probability mass function is a tool, right? So it tells us that the probability that 1 shows up is 0.375. Okay, and so how could we write that compactly using the notation, right? We might say P for probability, and we have this tool, this random variable, let R3 be our discrete random variable. So the probability that R3 is of the 3 people, the 3 helpers who are asked to show up, what's the probability that R is equal to 1? And we would say that it's 0.375. So we're part of the way there. So this is good. This is good, right? I mean, we want to know what's the probability that at least 2 show up, right? But this is a start, I think. right. So what is the probability that all three show up? Right, so we have this case where there are three helpers, and there's some likelihood that they will show up. There's some likelihood that they will not show up. And we want to know what's the probability that all three show up. So if you think about it, right, we want to use some of the tools that we have available. And so what we say is that, you know, R3 is the probability that or the number that show up out of three. Right? So there's three people, and they each have a 50-50 chance of showing up, and R3 is going to be the number that show up, that successfully show up. Okay? So we need to translate this into the mathematical language so that we can use the tools. So how do we get started? Right, what's the probability that all three show up? So probability, right? So what's the probability that something about the three show up, right? So we need to know, I mean, really, we only have the one random variable. So this is the probability that the number who show up is three in this case, right? So what is the probability that all three show up? We want the probability that when you count the number that show up, three show up, right? So this is how you translate a sort of natural language question into the, you know, mathematical formalism that allows you to answer the question, right? And so now we go, oh, what's the probability that all three show up? Oh, that's the case where the first one shows up, the second one shows up, and the third one shows up, right? So that's really the same as probability that, you know, we could say S1 shows up, S2 shows up, S3 shows up, but actually all of the probabilities are the same. They have the same probability, so we can just drop the subscript 1, subscript 2, subscript 3. We can just say probability to S, 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 right? So we know that that's equal to, you know, what is the probability of success, right? The probability of success is equal to 0.5 for the first one, and then times 0.5 for the second one, times 0.5 for the third one, right? So that comes out to, right, so this would be 0.25, right? And then times another one would be 0.125, right? But we actually kind of already have that over there, right? So that's the probability that all three show up, right? Because it's the first one shows up and the second one shows up and the third one shows up. And remember, when we had or, that was plus, right? And however, when we have and or intersection, that's multiplication. Okay. So now we want to know, what is the probability that at least two show up? So what is the probability that at least two show up? So we know that for sure, right? 100%, either one will show up, or two will show up, or three will show up, or four will show up. So, sorry, three. Zero will show up, none of them will show up, one of them will show up, two, or all three could show up. And so between the 0, 1, 2, 3, that's it. That's the sample space, right? So now we want to know, what is the probability that at least two show up, right? So we could say have our sample space of, 3, 2, 1, or 0, right? This is our entire sample space. So at least 2 will show up. So if 0 show up, is that it? No. That's not at least 2 show up, right? What about if 1 shows up? Is that at least 2 show up? No. Okay. So the probability that at least 2 show up, what if 2 shows up? Yeah, right? That would be at least, if 2 showed up, that would be yes, that would be positive for this case, or it would be true for this case that at least 2 showed up. And then also, what if 3 showed up? Would it be the case that, at least 2 showed up? Yes. Right? So what is the probability that at least 2 show up if we want to use our probability language, right? So what's the probability? So, okay, so for sure, it's asking about the probability, right? And then we really only have one random variable, right? So of these 3 helpers who could show up, right, we want at least 2, right? So we want something about 2, right? And we want it to be, right, greater than or equal to 2. Okay, does that make sense? So what is the probability that at least 2 show up? We translate that into probability, and then if we count the number of successes, we count the number that happen, we want 2 or more. Right? What's the probability that at least 2 show up? And so if we think about it, that's equal to the probability that or all 3 show up like before, or the probability that that the number that show up is 2. Okay, right? So the probability that R is greater than or equal to 2. Here, it's sort of impossible for 4 to show up, impossible for 5 to show up, really. So greater than or equal to 2 really means 2 show up or 3 show up, right? And remember, what do we do with OR, right? When it's AND, we multiplied, right? So OR is, we have to add, right? So OR is the union, right? And so with the union, that of course is add. So that means that we want this probability that R is equal to 3. So that's this 0.125 plus, and the probability that it's 2, probability that R equals 2 is equal to this 0.375, right? And so that means this probability that R3 is greater than or equal to 2 is equal to, so if we add the 5, that makes it 10. So carry the 1, so that's 8 plus 2, that's 10, that's a 0 again. And so if 4 plus 5, so it's equal to a half. Okay, so again, also this is 1/8, and this is 3/8. So 1/8 plus 3/8 is 4/8, which of course is equal to a half. Okay, so what's the probability that R3 is greater than or equal to 2? Okay, that's a half. Okay, so that's the probability that at least 2 show up. What is the probability that 1 or 2 show up? Right? So here it's really a little bit easier. The probability that R3 equals 1, or right, the probability that R3 equals 2. What's the probability that 1 or 2 show up? So again, or is a union or a plus, right? So then we would have the probability that R3 equals 1 plus the probability that R3 equals 2, right? And again, they're mutually exclusive, so we do not need to subtract the intersection, right? Because the intersection is 0, because they're mutually exclusive. Okay, mutually exclusive. So basically, we take the probability that R is 2, which is 0.375, and the probability that R is 1, same, 0.375, and we add them together. So 0.375 plus 0.375. If you remember that this is actually 3/8, we're adding 3/8. So this gives us 6/8, which is the same as 3/4. So that's equal to 0.075. 0.075. Okay. So maybe we'll put a box around that. Okay. So now the question is, how many would you expect to show up? So in this case, how many would you expect to show up? And remember that the definition of the expected value, or the mean, or the expected value, it has this form here. However, there is a special case where in the binomial case, it's just NP. Okay, so how many would you expect to show up? It's just NP. So we would expect NP to show up where N is 3 and P is 0.5. So that's equal to 1.5, right? And, hopefully that makes sense, right? Because if it's a 50-50 chance of showing 1, so just now, our example is 3, but in order to try to understand that you just take the number times the probability to get, 1.5, why should you expect this? Well, imagine instead of asking about all 3, imagine that you say, well, what if one of them, what do you expect if one of them would show up? Well, a half, right? Because the probability is 0.5. So, either one is going to show up or one is not going to show up. And so you'd say, well, 50-50 chance that none of them show up, or 50-50 chance that one will show up. Okay? And so now it's not just 0.5 for one of them, but it's 0.5 for all 3. And so you take the 3 times the 0.5 and you get 1.5. And so if you look here, the question above is, what is the probability that 1 or 2 show up? And we see that it's huge, 0.75. So there's a 75% chance that 1 or 2 of them will show up, right? Why? That's because that's the expected value. And so if we look, the expected value is right there, 1.5. Mu is equal to 1.5. And so we would expect 1.5. Of course, it's people, so it's 1.5 persons is not going to show up, right? So it's either going to be, well, it's most likely that you expect 1 or 2. That's what you would expect, 1.5, right? 1 or 2 will show up. And 1 or 2 will show up with a probability of 75%. So it's really likely to get 1 or 2. But if you really need all 3, may not get all 3, right? You may not get all 3. Okay, so let's look at another example here, right? So here we have 3 customers in the customer service line, right? So suppose that there are 3 customers in a customer service line. From past experience, from empirical evidence, you have data and you analyze your data. So from historical empirical records, we know that the probability that a customer will need to talk to a supervisor is 10%. Okay. What is the probability that at least one of the 3 customers in line will need to talk with a supervisor? Right. And again, you may be if there's 3 customers in this customer service line, should you have the manager sort of drifting around? Well, no, I think that, well, as we'll see, right? Or, you've got 10 customers in the customer service line. Chances are at least one of them is going to need, and so the manager should sort of drift over there. You might put in a call, hey, can you hang out near the area so that if we call, if you're needed, you can get there quickly, right? So to help make decisions, right? How to run the business, right? So suppose that there are 3, right? Notice that the sample space looks the same as the wedding helper case. In fact, the values of the random variable are the same. Right? The random variables, sample space is the same, the random variable is the same. What's different? What's different is that we're connecting up a different distribution to the random variable, right? We're connecting, we're hooking up, we're using a different random variable, a different member of the binomial distribution. It's a different probability distribution. We're connecting a different probability distribution to the reusing the random variable, but we're hooking up a new random variable to it, so it's different. So what we need to do is we need to calculate these values of the probability mass function, right? And so the first one is easy, and so we're going to use that to determine what is the probability that at least one of the 3 customers in line will need to talk to the supervisor, right? So what's the probability that all 3 will need to talk to a supervisor, right? And so it's 1/10 for the first one, and 1/10 for the second one, and 1/10 for the third one, because the first one needs to talk to the manager, the second one needs to talk to the manager, and the third one needs to talk to the manager. So we know that's intersection, and intersection can be done by multiplication, right? Because we assume they're independent, right? So this is actually 0.1 times 0.1 times 0.1. So 1/10 times 1/10 times 1/10, right? And that, of course, is equal to 0.001. So 1 in 1,000. Pretty unlikely that all 3 of them will need to talk to the customer, or talk to the manager. Okay. So in that case, so let's back down 1 notch. Because this one is actually 0.001. Okay, so we're filling in the probability mass function, because when you do these kinds of problems, it's nice to have the whole probability mass function in your back pocket. Okay, so as the next one down, suppose instead of all 3 needing to talk to the manager, 2 of them need to talk to the manager, right? The number of successes in the 3 is 2. Okay, so well, we know that from here it's either the first 2 need to talk to the manager and then the last one doesn't, or possibly the first one and the third one does and the second one doesn't, or maybe the first one doesn't, but then the last 2 in sequence need to make the 2, right? So and because we know, thinking ahead a little bit, that we're going to multiply, we need to multiply 0.1 for a success and then another 0.1, and then instead of being a third 0.1 cubed, it's going to be 0.9. So one of them is going to turn out to be a 0.9. Okay, and so we know that there's 3 of them. So instead of writing 0.1 times, or I'll just write it out here, times 0.9 plus 0.1 times 0.9, times 0.1 plus 0.9 times 0.1 times 0.1. Okay, I kind of wrote that whole thing out, but really what we want to do is we want to just say there's three cases where it's 0.1 maybe squared times 0.9. Okay, because the square will take the 2 of them, and then there's just a 1 by itself. Okay, and so if you work that out, 0.1 is squared is 0.01. 0.01 times 0.9 is 0.009, and then times 3 is 0.027. Okay, 0.027, and so let's put that in there, 0.027. Okay, and then the next one down. The next one down is actually similar to this, except instead of being 2 of the 0.1s and only 1 of the 0.1s, okay, it's kind of the opposite, where it's 2 of the 0.9s and then 1 of the 0.1s. So again, we have 3 of them, and we have the 0.1 by itself, and then now we have the 0.9, the 0.9 squared, Okay, so this is 9 squared, so 81, 0.081, and then we have to multiply it by 0.1, so that's 0.081, and then we times it by 3, so the 81, and so that becomes 3 times 1, and then the 3 times the 0.8 is 24. Okay, so that comes out to be 0.243. So this is 0.243. So at this point, when there's only one left, we know that the sum of all of them is 1, right? So actually we should just go back and check that, right? So I mean, it's true, right? Because it's the entire sample space. So this 0.125 plus 0.37, that's 0.5, right? And then again, 0.375 plus 0.125, that's another 0.5. So 0.5 plus 0.5 is equal to 1, right? So technically speaking, excuse me, if we only have the one puka, we only have the one that's missing, the one hole, the one empty space, we could do 1 minus all of those, and then we would come up with the answer, right? So this is actually 0.70, 0.27, right? Because that makes 10, that makes 7. And so what we could do is this one is going to end up being 9, right? And then this other one is going to be 6, 7. So that should be a 2. And then if we make that 7, it should add up to 1. And so just by doing the, say, 1 minus 0.001 plus 0.027 plus 0.243. Okay, but we can actually continue to do it this way. In fact, it's just the opposite of this one, right? Because here it's, and there's only one case, so we don't have this coefficient of 3. So we just have the 0.9 cubed, right? So if you cube it, it turns out that it's 0.729, right? So let me see. We can just do 0.9, and then we do y to the x, to the exponent. So the number that was there, 0.9, becomes y, and then now this is x, the last one that we put in, and that gives us the 0.729. Okay, so the question is, what is the probability that at least one of the 3 needs to talk to the supervisor? Okay, so remember, here is our sample space. So what if 0 need to talk to the supervisor? Is that at least one? No, right? No. So what if one of them needs to talk to the supervisor? Right. That's it, right? Yes, at least one. So if 2 of them, then that's at least one. Then 3 of them, then that's at least one, right? So the probability that R3 is greater than or equal to 1 is equal to 0.001 plus 0.027 plus 0.243, and that's equal to probability that R3 greater than or equal to 1 is equal to, oh yeah, so this 2 is 0.70, and plus that is 0.701. 0.701. Something like that, right? No, sorry. .271. Yeah. Right, because this would be 0.6, 0.7, yeah, right. Okay. So is there a way to, can we work smarter, not harder. Can we work harder, not smarter? And so, you know, how hard is it to add three numbers? Well, it's not that hard to add up three numbers, right? But, you know, is there any shortcut that you could take, right? And so, well, you might ask about what's the complement. So anytime you find yourself like adding up a lot of probabilities, you might say, well, is there a way that the opposite way, if I go the back way, you know, go in, you know, back door, could that be a shortcut? And so in this case, it is, because the complement, right, the probability of R3 greater than or equal to 1 is equal to 1 minus the probability that R3 is equal to 0. Okay, the probability that it's 1 or more is equal to the total probability minus the 1, or the first case, right? Minus the probability that none of them need to talk to the supervisor, right? So if you do, of course, 1 minus this 0.729, it turns out that equals 0.271, so that checks out. So if you thought of taking the backdoor approach, that could have given you the other approach, right? The backdoor approach, that could have given you the same answer, the correct answer, with 1 subtraction, right? So instead of having the addition of 3, we just have the 1 subtraction, okay? So now the last question is, what is the expected value? What is the expected value, right? So we want to know E of R3, right? And so remember that there is the definition of the average, there is the definition of the expected value, and so you have to like add up all these things. However, with the binomials, there's a shortcut. With the binomial distribution, there's a shortcut. So it's equal to NP, which in this case is 3 times the 0.1, which is 0.3. Right? So how many do you expect? That's pretty close to 0, right? And so in fact, you can see that the probability of 0 is 0.72, right? That's almost 3/4, right? 0.75 would be 3/4. So very, very, very high probability that none of them would need to talk to the supervisor, right? And, you know, if we could, we should have, maybe it might have been nice to have a little sketch of the comb function, but we can just draw in the comb function of the probability mass function, right? It would be like 0.75 for 0, 1 would be like 1/4, and then 2 and 3 would be like that. And then the cumulative distribution function would be, you know, a huge step up over there, and then a tiny little step, and then a tiny little step, and then a tiny little step at 1, 2, and 3. So there'd be a big step, and then, you know, about 0.25, quarter of the way, right? So between these two, you're already at about 3/4, and just each tiny step is a little bit more. So the comb is really drastic, right? Okay. So now we continue, and suppose that there are 5 guests who've checked in at the front desk. there's a 95% chance that their luggage will be delivered to their room within 5 minutes of their arrival. What is the probability that all 5 of the guests will have their luggage delivered within 5 minutes? So here, as we mentioned, it would be really nice to have the entire probability mass function in your back pocket, right, to look at. But if the question is, all 5, you kind of luck out, right? Because you know that you're going to have to do kind of one of these things really for 5. So instead of being like this, how many cases, like 2 times 2 times 2, that's 8. So times 2 again would be 16, okay, and then times 2 again would be 32. So we would have half the page, right? Instead of 8 lines or 16 lines, quarter of the page maybe, we'd take maybe half the page with 32, right? So a lot of cases to keep track of. And so maybe, but see, this is just asking about all 5. And so if there's all 5, there's only one way to do that, right? There's only one way to do that. So we know that, so here I guess we'll say let T equal number of on time, I guess we'll say deliveries. Okay, the number of on-time deliveries. And so we want, what is the probability that T is equal to 5? And so we know that's actually, instead of using 0 on time, we'll just say good. We'll say, good 1, good 2, good 3, good 4, good 5. And then again, instead of doing the 1, 2, 3, 4, 5 subscript, since they're all independent, we know they're all equal, and so it doesn't matter. So I'll just leave them like that. So probability that they're all good, right? And so that's actually really this 95% chance that they're delivered on time. So that's 0.95 to the 5th power, right? And what's that? Let me see here. If we, oops, here. So we want the 0.95. And so again, we're going to use the y to the x function or key. So we push that. So now it becomes y. And this other value that we enter, the exponent, becomes the x. So we do that. It's 0.773. Is that right? Equal, let me see if I can copy, and then can I paste that? 0.773. That didn't work out too well. 0.774, say 0.38. Oh. I guess it could possibly work out. Oh, never mind, we got it. Oh. Oh, yeah. Okay. So next, in this case with 5 guests, how many would you expect to have their luggage on time within 5 minutes? So now it's how many would you expect to have their luggage on time, right? And so this one is the expected value. Expect, right? How many would you expect to receive their luggage on time, right? Given this process characteristics, parameters, right? So we're looking for the expected value of t. So again, remember that we have a binomial. Oh, we didn't say binomial. Oh, yeah, sorry. So we should say here's our t, and t is distributed as a binomial with 5 trials and 0.95 probability of success, right? 0.95%, sorry, 95%, which is 0.95 decimal, okay? So what is the expected value? We know the expected value is NP, so that's 5 times 0.95, and so if we can just check that, so 0.95 times 5 is equal to 4.75. That was 4.75, right? 4.75. And so, you know, what is the probability of 5? The probability of 5 is 0.75, so it's really very likely. And so here, you're more likely to have 5. It's clearly between 4 and 5, but really much closer to 5. So you really expect almost 5 of them all the time, if it's 5, to get the luggage delivered on time. So now what is the probability that 4 or 5 guests receive their luggage on time? Okay, so now we have to work a little bit harder, right? Actually, we could use Excel. Okay, so it turns out that there is a function in Excel called binomdist. Okay, binomial distribution. And so the first argument that goes to the function is number s. So what do you think that is? That's like the number of successes, right? The number of successes, right? So the second one that goes in is the number of trials. So that's like n. So that's n, okay? And so after you do that, comma, the next one is the probability S, the probability of success, right? That's the probability of success, okay? And so the one after that, it's, do you want the cumulative distribution function? So it returns a probability mass function. So if you set it false, then it equals the probability mass function. Whereas if you set it true, then it returns the value of the cumulative distribution function. Okay? So we could get it through Excel. On the other hand, you know, the 4 guests, so probability that what we really want is the probability that t is equal to 4, you know, or the probability that t is equal to 5. But we already know 5, right? We already know the probability that is 5, and so really we just need to find the probability that it's 4 and add them together. And oh, by the way, Excel just told us the answer. But you know, we might want to try to think about it, right? And so in order for let's see, good, you know, for there to be 4 guests who got their luggage on time, that means that one of them did not get their luggage on time, right? So it could be the 5th one. On the other hand, it could be the 4th one. On the other hand, it could be the middle one, or it could be the 2nd one, or it could be the 1st one. Oh, sorry, this is not. The 1st one didn't, and then whew, all the rest in a row are received. So this is like 1, 2, 3, 4, 5. So it's actually no accident that there are 5 and there's only 1. You know, if you pick 1, say, then of the 5 could be the last one, could be the second to the last one, you know, middle one. So it doesn't matter which order the no was in the batch of 5. One of them did not receive their luggage on time. Okay, so it's really going to be 5 times this 0.95 to the 4th power times 0.05 to the first power. Okay? And so if we do, say, the 0.95, and then we do the 4, okay, so now we have this piece. Okay, so now we have to say multiply it by 0.05, and now we have to multiply it by 5. And that's actually what Excel is doing. Okay? That's actually what Excel is doing. So you can do it on the calculator. So let me see. That's actually, how should I write this down? P that t equals 4 is equal to 0. Let me get it from this page. 2036, I guess. 20. Let's just keep it to 3, not 3. 204. We'll just round it to 3 places. Okay. So the answer, right? P t, I guess we'll just say greater than or equal to 4, is equal to this 0.774, right, from before, plus this 0.204. So that's equal to 0.978. Okay, so you're really likely to have 4 or 5. And in fact, the mean is closer to 5, but really 4. So you got a 97% chance that 4 or 5 are going to get their luggage on time. Okay, so that's the a computation with the binomial distribution. Okay, so now there's a field of math called combinatorics, which is some counting methods. And on the calculator, that would be this exclamation point here, which would be x factorial. And then the other one would be, the one below that would be permutations. There's NPR. And then the third combinatorial function, shall we say, is combination, which is NCR, which is the third one. So that's factorial, permutations, and combinations. And so arrangements, permutations, and then combinations. Okay, and so what we want to learn about all of them, but really the combinations are the ones that are pertinent or relevant to the binomial distribution. Okay, we'll say a little bit more about that later. But the combinations have to do where the order does not matter. The order does not matter, okay? And so this is related to a concept called Pascal's triangle. So maybe some of you have seen Pascal's triangle, maybe some of you haven't seen it. So basically this is Pascal's triangle. So you start with 1, the first row has 1, and then the second row, or the 0 row, has 1, and the next row down has 1, 1. So that's how it gets started. Okay, so how do you do the next row? Well, you bring this one down and you bring this one down there, and then this one you get by adding those two, and you put the answer over there. Okay, now you're done. Okay, so to go to the next row down, basically copy this one, you copy this one. Okay, to get this space, you add these two, there's 3. So 1 plus 2 is 3, and then 2 plus 1 is 3. Okay, then you got all of them, you're done. Okay. The next row, again, you copy the one down, you copy that one down, and then for this one, you take this 1 plus this 3 to give you 4, then you take this 3 plus this 3 to give you 6, then you take this 3 plus 1 to gives you 4, and then you're done. Okay, so that's the first few rows. Next row down, I think you figure it out, right? You just copy that down, copy the 1 down. Now, to go for that one, you do the 1 and the 4, you get 5. And then to get the next one, you do the 4 plus 6 gives you 10. Next one, 6 plus 4, other way around, gives you 10. And 4 plus 1, the other way around, gives you 5 again, as before. And then reach the end, you're done. Okay, and then it goes on and on and on. So these coefficients are actually important for the binomial theorem, the binomial distribution. And they also are these combination coefficients, okay? And so that's actually what we want to do next, because that will allow you to calculate, excuse me, the terms in the binomial distribution. So here's an example of the binomial family with p is, say, equal to 0.5 and p is equal to 0.6. Okay, and notice that it's really not so difficult to do it with the Excel function. Okay, and if you look, it's the second position. So this would be b, say 2, and then 0.6. So this would be so there's like several. So if you wanted to practice, here are some answers. But in the homework problem, you actually, I think you may have to get a rather large probability mass function. And so we'll learn about this later, but for now, you should think about using the binomial distribution. And so you can see that this is n, this is p, this is n, this is p, this is n, this is p. And then here, these are the number of successes. So do you want to have 5 successes, or do you have no successes? That gives you that one. And then using this will actually help you to quickly get the probability mass function. And then we'll do more details next time. Okay, so we'll see you next time.